To further analyze the hyperbola, we're going to need to come up with an equation for a hyperbola. So to do that, let's start by putting a coordinate system on our hyperbola. So since the hyperbola has a center, it's nice to put the origin of the coordinate system at the center. And it seems like you would either want to put the line between your foci either along the x-axis or along the y-axis. Here I've put it along the x-axis. We'll see later what happens if you put the y-axis along the foci. Okay, remember our equation for a hyperbola looks like this. The distance from f1 to your point, remember this is for any point on the parabola, P, the distance from f1 to P minus the distance from f2 to P, the absolute value of that has to be 2a. And we figured out a sort of geometrically what this distance a means. It's the distance from the center to one of the vertices. Remember, the vertex of a hyperbola is this inner point, and there are two of them. So the distance from the center to a vertex is a, and we called the distance from the center out to one of the foci, we called that c. So using this setup, we can write down the coordinates of these points. So P is our variable point, so we're going to call that x comma y. And then the foci, well, F2 here it's on the y-axis. So, I'm sorry, on the x-axis, so its y-coordinate is 0. And its c units to the right of the origin, so its x-coordinate is plus c. And then for F1, of course, it's the same, except it's to the left of the origin, so x-coordinate is minus c. All right, now it's kind of clumsy to have these absolute values here. So just for the moment, let's just forget about the absolute values. And the reason that we can do this is because, well, this whole calculation that we're about to do, parenthesis here, this whole calculation that we're about to do to fix the fact that we actually do have absolute values here, we would just do the whole calculation again, but with an extra minus sign in the front of everything. So, of course, how it all works out will be pretty much the same whether there's whether this absolute value sticks on an extra minus sign or not. So it won't actually change anything conceptually to just erase the absolute values for the time being. Okay, so here's our equation. Let's write both of these distances as square roots. Since we have a coordinate system, we can just use the distance formula. So the distance from F1 to P is the square of the difference in x coordinates. So that's x minus negative c, so x plus c squared, plus the difference in y coordinates, but that's y minus 0, so that's just y squared. Okay, minus the distance from F2 to P, so that's the square root of x minus c squared plus y squared. Okay, and that's 2a. So we're going to want to get rid of these square roots just to simplify this equation, because this equation is so complicated that it's hard to really know what it's saying. It's not clear how to use it. But, you know, it would be nicer if there weren't square roots. So let's get rid of the square roots. To do that, we're going to take this part and move it to the right. So we get square root of x plus c squared plus y squared. So all of that in a square root equals 2a plus the square root of x minus c squared plus y squared. Okay, and to get rid of some square roots, we need to square both sides. Okay, so on the left-hand side, the square just undoes the square root, and we get x plus c squared plus y squared. And then on the right-hand side, the stuff inside of this squaring has two terms. And so we have to multiply all of this out. Remember, you get the first part squared plus twice the product plus the second part squared. So first part squared is 4a squared plus twice the product, so twice 2a times the square root, so that's 4a times the square root part, so square root of x minus c squared plus y squared, plus the second term squared. But the squaring the second term just undoes the square root, so we get x minus c squared plus y. Okay, it looks like this y squared and that y, sorry, this should be y squared here. So that the y squareds on both sides cancel. All right, and it looks like if we multiply out this x plus c squared and x minus c squared, some more stuff will cancel, so let's do that. So x squared plus 2cx plus c squared equals 4a squared plus 4a times the square root of x minus c squared plus y squared plus, okay, now we're multiplying out this squaring, x squared minus 2cx plus c squared. And then we can subtract x from both sides. That gets rid of, subtract x squared from both sides. That gets rid of these. And then subtract c squared from both sides. That gets rid of these. And then add 2c to both sides. 2cx to both sides. And that's going to move this minus 2cx to the left. So now we have 4cx equals 4a squared plus 4a times the square root of x minus c squared plus y squared. Okay, and it looks like we can divide everything by 4, so let's get rid of those 4's. All right, now we got rid of one square root, but we still have a square root, so to get rid of this remaining square root, we just need to isolate it and then square both sides. So let's subtract a squared from both sides. We get c times x minus a squared equals a times the square root of x minus c squared plus y squared. Okay, now we can square both sides. On the left, we're going to get c squared x squared minus 2a squared c times x, yes, plus a to the fourth. All right, and on the right-hand side, we get a squared times this whole square root squared, and that just undoes the square root. So x minus c squared plus y squared. Okay. On the right-hand side, so the left-hand side, let's see, what could we do? Let's leave the left-hand side alone for now. So c squared x squared minus 2a squared cx plus a to the fourth. On the right-hand side, let's start multiplying out things. So we'll distribute this a squared. We get a squared times this x minus c squared, and that's x squared minus 2cx plus c squared. And then distribute the a squared to y squared, so plus a squared y squared. All right, and now I guess we need to distribute this a squared. So c squared x squared minus 2a squared cx plus a to the fourth equals, all right, a squared x squared minus 2a squared cx plus a squared c squared plus our final a squared y squared. Okay, now for a start, we can add 2a squared cx to both sides, and these are gone, so that seems nice. Let's gather up all the terms with variables on the left. So that's this term, and this term. So these are all going to go left. And let's gather up all the terms without x or y to the right. So that's this term and this term on the right. Okay, so on the left we have c squared x squared minus our a squared x squared minus, right, this a squared y is moving to the left, so minus a squared y squared equals, and then on the right we have this a squared c squared minus a to the fourth. Okay. This looks like it's getting better, but I see there are some common terms, some common factors we can factor out. Oh, I'm missing a squared right there. In these first two terms, we could factor out the a squared, so that gives us c squared minus a squared all times x squared minus a squared y squared equals, and on the right, looks like we could factor out a squared. So that's a squared times c squared minus a squared. Okay. Now, actually, this is kind of looking similar to an ellipse, except for this minus sign in the middle. And a trick that we saw with the ellipse is, right, because factors, these coefficient factors on the left-hand side show up multiplied on the right, we can simplify further by dividing everything by a squared times c squared minus a squared. So here, a squared times c squared minus a squared, and dividing by a squared times c squared minus a squared. Okay, so on the left, for the x's, for the x squared term, these simplify away, and we're left with x squared over a squared, that's promising, minus, then for our y's, the a squareds simplify away, and we get y squared over c squared minus a squared. And then on the right-hand side, well, everything simplifies away, and we're just left with 1. Okay, so this does indeed look very similar to the equation for an ellipse, except there's a minus sign in the middle. But for the ellipse, we had some nice interpretation of what this c squared minus a squared was. It wasn't, I think it was a squared minus c squared in the case of an ellipse, but this time we got c squared minus a squared. Let's see if we can come up with a geometric interpretation of what that is. So remember, our hyperbola looks something like this. Ooh, terrible, terrible hyperbola. We have foci like this, and A is this distance here. Okay, C is the distance out to a focus from the center. And this new quantity, c squared minus a squared, sort of by analogy with the ellipse situation, we might expect that this is the square of something, right? I kind of have the notation set up to make you think that there's a b in here somewhere. So let's name this quantity. We're going to call this b squared. And then we can move a squared to the other side. We get c squared equals a squared plus b squared. And what this is telling us is that in this diagram, if we draw a right triangle with one side being a squared, with one side being a and the hypotenuse being c, right? This looks like the Pythagorean theorem for a right triangle. So if we can draw a right triangle with one side being a and the hypotenuse being c, the other side will be b. So what we could do is sort of take this length c and kind of, that's going to be our hypotenuse, remember? Just tip it upwards until it goes like this, and the upper right end of it matches the end of A. So now we have a right triangle here whose hypotenuse is C and whose bottom side is A, and that means that according to this equation, the right-hand side must be B. And so that's what this denominator is here. It's the square of the right-hand side of this triangle. Notice this right triangle is the one whose bottom side goes out to the vertex of the hyperbola, and then the hypotenuse is the length c. Okay, so that means that this equation is x squared over a squared minus y squared over b squared. And this was a hyperbola whose foci are c units along the x-axis, and c squared is a squared plus b squared. Okay, so that's if you put the foci of the hyperbola along the x-axis. If you put them along the y-axis like this, then the hyperbola is going to look something like this. And the only thing that changes in this whole calculation is, it turns out that where the minus sign is the one thing that changes. So you get y squared over a squared minus x squared over b squared equals 1, and still c squared is a squared plus b squared. So these are the two versions of the equation for hyperbola. Notice that where the minus sign is sort of shows you where the gap in the hyperbola is. If the minus sign is on the y squared term, then there aren't any y-intercepts. If the minus sign is on the x squared term, there aren't any x-intercepts.